concentric shells A and B are given charges Q1 and Q2. What will be the potential electric field everywhere in the region, and also the potentials of individual shells and also the potential difference. Everything has to be determined. Now, do we know potential due to shell? What we discussed for conducting spheres, same thing. Can you recollect conducting sphere? What will be the potential everywhere inside the conducting sphere, charged conducting sphere? Will be that on the surface. So same thing happens with the shell also. So what all we discussed for a conducting sphere, the potential electric field, the same thing applicable for the shell also. Hope everyone is able to recollect. If you forgotten, go for the notes, turn the pages, no, there you can see clearly. Fine. Okay, no, it is given like this. So how to calculate that potential? So to calculate potential, I'll take help of superposition principle. To calculate the field, I'll take help of the Gauss law. These are the few things which I'll be taking care here. Let me hide it. Yeah. Yeah. Now we'll proceed like this. So first, actually, the shells are given charges. You see that one. This is given Q1 and this is Q2. This charge Q1, what it do? It will induce charge. So overall, the final the situations that will occur is here charge Q1. It will induce a charge minus Q1. What is the charge on outer surface of shell? Q2, no? The total charge will become Q1 plus Q2. This will be the charges on each surface. Okay, the first problem, no? Okay, we'll start like this. What is surface charge density here? I'll call sigma 1. What is the surface charge density here? I'll call sigma 2. Let this be sigma 3. Can we calculate sigma 1? Sigma 1 should be equal to Q1 by 4 pi A square. What is the surface charge density of the outer shell? Q1 plus Q2 by 4 pi B square. What is the surface charge density of inner surface of the shell B? Sigma 3 equal to minus Q1 by 4 pi B square. Agreed? This one? So this will be the charges. Now he's asking to get the potential. So now whether you consider this induced charge or not, you're going to get same answer. I'm going to change there's a one part. Okay, now we'll take the, so every time you need not to go for this as they're thin shells, no, you need not to bother about this induced charge. Even then you'll get the same answer. Okay, looking at this diagram, we'll find. First, we'll choose the point. Let me choose the point P1. Now, what shall I do now? So here, this is the R1, or shall I write R? So where is the point? This one. So there the electric field I want. So what shall I do? I will draw a Gaussian surface. Then where this charge plus Q1 will be on the surface of the shell A, plus Q2 charge will be on surface of shell. In fact, the charge will be like this. Here plus Q1, here minus Q1, and what about here? Q1 plus Q2. They'll be distributed uniformly. Actually, we have seen all that one. Then when I draw a Gaussian surface, where do this whole charge will appear? As it is the charge is distributed symmetrically with respect to center of Gaussian surface. So where the whole charge? Okay, I think there's a first problem. Let me draw the Gaussian surface. What is this? This is a Gaussian surface. And look at that. These are symmetric charges. The charge is distributed symmetrically. Then what happened is the whole charge plus Q1 on shell A will appear at center. Even this also appear at center. No, sir. Now I look at this and draw it. Okay, then also no problem. Plus Q1 minus Q1, Q1 plus Q2. How much of net charge at center will be Q1 plus Q2? So now we know what is the electric field strength. EP1. This should be equal to K Q1 plus Q2 R square, where R should be greater than B. The point lies. Similarly, what is the potential? K Q1 plus Q2 by R. Okay, I agree this. I'll come to the later. Okay, let me choose the point now somewhere inside. Huh? Let the point be the point P2. What about the electric field and potential? So let me write this as distance. Already A is there, no? I'll write R. Let me write R only, no problem. Where what is the condition for R? R should be less than B and greater than A. What about the field strength there? First EP2. What I'm going to do is I'm going to draw I don't have a space now. I'm trying to accommodate everything here. I'm going to draw a Gaussian surface here. If I draw a Gaussian surface, then what is the net charge enclosed? Will be only Q1. Okay, I think, yeah. I'll slide down. No problem. Yeah, we'll take this one. There's a first diagram for first problem. No, I'll try to give detailed explanation. This is a Gaussian surface. Tell me, like, what is the dotted line? Understood? It's the Gaussian surface here. What is the net charge enclosed by Gaussian surface? Only the charge Q1, and that too, it's the charge is distributed symmetrically with respect to Gaussian surface. So where do all this charge plus Q1 will appear to be at center? Then similar to like a point charge, what is the field strength will be? KQ1 by R square. Now you can ask very best question here. Sir, this charge is there. Will it produce field anything? Yes, it will produce. Even the symmetric charge will also produce. Due to symmetry, distribution of charge Q2 on shell B, the net field at point P2 due to Q2 will be 0. Don't say it will not produce field. The net field contributed by the charge Q2 on shell B at P2 will be 0. You have to write this. You can't listen. Huh? If you just listen, it's not like some TV serial. You can't just listen. Some things which I'm stressing are very fundamental. Immediately you should scribble it in your notebook. So what is the point P2? What is the condition? The charges on all surfaces will contribute field at point P2. Then the net field at point P2 is but only due to Q1. Why not due to Q2? The resultant means even if you take this particular sector, it will contribute field. This other sector will contribute to equal and opposite field. Net field will be in fact 0. The net field, the net electric field at point P2 due to charge Q2 on shell B will be 0. There's a condition. Then only Q1 is what contribute. I'm writing. So what is the condition for this R? R should be less than B. You're supposed to think, analyze, no, just only mere listening not possible. No? Okay, this is about the electric field. What about the potential? Potential is due to superposition of surface, due to superposition of charge on all surfaces. When it comes electric field, only charge enclosed by Gaussian surface will contribute the net field at point P2 on the Gaussian surface. When it comes potential, due to superposition of charge on all surfaces. So how to write expression for potential? Potential is given by first we'll go for superposition. Assume that only charge on shell 1 is present. Then at what distance it is? The point P2 lies outside. Go for conducting sphere. What is the potential outside a conducting sphere? KQ by R. It's similar to this one. KQ1 by R. Then if shell inner shell is not there, only outer shell is there. What is the potential? Go for conducting sphere. What is the potential inside the conducting sphere? That on the surface. So same thing for shell. So now assume that inner shell not there, only outer shell is there. Then what is the potential on outer shell? KQ2 by B. And that should be the potential everywhere inside. So the formula will become KQ2 by B. I think this will be very important. When it comes field, we took Gauss law. Net charge enclosed by the Gaussian surface will contribute field there. When it comes potential, what we did, we took superposition. The charge on all surfaces will contribute here. Q1 will contribute potential, Q2 also will contribute. Point P2 lies outside this shell. So therefore what will happen? KQ1 by R. Then you assume that this inner shell not there. Then where this point P2 lies inside the shell, and what is the potential inside the shell? That on the surface. Anybody having doubt, please clarify. Strictly, there is a condition for R. R should be less than B and greater than A. Okay, so this is about the potentials. Okay, now I want potential somewhere inside. So let's get into this one. No. Okay, this is not needed now. Where is the point? No, the point will go inside the shell A. At point P3. Shall I write 0? Strictly, what is R? R is less than E. What about potential at point P3? We should do why 0? Because where you are drawn Gaussian surface inside the material A, like inside the shell A. So what is the net charge enclosed by Gaussian surface? 0. So electric field is 0. Then potential at this point, we should go for superposition. Then first only due to shell 1, shell A. Now where the point P3 lies inside the shell A, what is the potential inside the shell A? That on the surface, similar to conducting sphere again. So therefore the potential should be KQ1 by E. Then afterwards, only due to shell B. Assume that shell 1, shell A is not there. So where the point P3 will lie inside the shell B. Then what is the potential inside the shell? That on the surface. So KQ2 by B. Shell or conducting sphere, both are same. You can write in your notebook. Electric field and potential, what all we determine for conducting solid conducting sphere is similar to that of the shell. Thin conducting shell. What will be present here? Air, vacuum. Only the iron is present here. This pink color is what? Iron. Concentric shell, able to assume all of you, football, volleyball, made up of some iron, thin iron sheet. We are discussing of that kind here. So if you are getting confusion, write it. This is iron. This is a copper. No, okay, nothing wrong. Huh? You can take help of such things. I'll write it here. Okay, conducting also, it may not flash you much. Okay, this is about the field potential at various points. So now I want potential of individual shells. I need fresh one more page. Just it's a procedure method. Already we have done a little bit in gravitation, but here a little bit more cases will come. Okay, no, I want the potential of each shell. What shall I do?